Okay, engineers, now Laplace inverse. Now let's see how many formulas do we have. So far we have the Laplace transform of t to the power of n, which is n factorial divided by t to the power of n plus 1. The Laplace transform of the exponential of 18, 1 over s minus a. The Laplace transform of the sine of kt, k over s squared plus k squared. The Laplace transform of the cosine of kt, s over s squared plus k squared. Okay, now the inverses. There is no definition of the inverse. The inverse is just the opposite. So I'm going to write here the inverse, okay? So the Laplace inverse with minus 1, indicating not 1 over the Laplace transform, instead is the inverse operation. The Laplace inverse of 1 over s minus a is just exponential of 18. The Laplace inverse of k over s squared plus k squared is equal to the sine of kt, and the Laplace transform inverse of s over s squared plus k squared is just the cosine of kt. Okay, so in the end, engineers, it's just looking at the inverse, is just doing the opposite operation. Now, what about this one? Okay, the Laplace inverse of 1 over, no, sorry, this is s. Sorry, this is s. My mistake there. 1 over s to the power of n, so it's going to be t to the power of n plus 1 over n plus 1 factorial. So that is the formula. No, sorry. Minus 1 here, minus 1, and here, minus 1, because we said it is the opposite operation, right? Okay. By the way, here, the formula of the derivatives, the Laplace transform of the first derivative is equal to s f of s minus f of 0. The Laplace transform of the second derivative, s squared f of s minus s f of 0 minus f prime of 0. And the Laplace transform of the third derivative is going to be s to the power 3 f of s minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. Okay, now what are those f of 0, f prime of 0? F of 0, f prime of 0, f double prime of 0, they are the initial conditions that we usually use to find the values of the constants. Okay, I don't want to go there because we haven't solved a differential equation. Now, why we are looking at these formulas and this procedure now for the differential equations? Well, this is the process that we are going to use. Imagine that you have this differential equation, second derivative of y respect to the t squared plus derivative of y respect to the time plus 3y equals 0. So that is the differential equation, second order differential equation with constant coefficients. Now, the purpose of this, why we are looking at the, we want in the end the solution. And we already know how to solve this, but we are going to take another way to solve the same by using the Laplace transform. So what is going to happen here is that you are going to throw the differential equation into the tortillas machine of the Laplace transform, and you are going to get some f of s and whatever. So this is the t domain, and here is the s domain. The beauty of the Laplace transform is that here there is no derivatives. Okay? So here the problem is very complex because you have derivatives and you cannot make factorization because you cannot factorize the y from here, here, and here. But because in the S domain there is no derivatives, then it becomes only a algebraic problem. Only to find capital Y of S. So that is the advantage. You don't have derivatives. In the S domain, you have only an algebraic problem where you have to just find the value of capital Y of S. It's very easy. Here is very difficult. Here is very easy to solve. However, on this S domain, what you have is very easy to solve, but is in the S domain. So what you have to do, engineers, is go to the Laplace inverse tortillas machine, the Laplace inverse operation, and you throw here your capital Y of S, and you are going to get Y of t. This Y of t happens to be the solution. Alright? So that's what we are going to. This is why we are looking at the Laplace transform, another method to solve, to get to the solution, by taking the Laplace transform, solve it in the S domain, and then bring back the solution to the T domain. So this is more like another dimension. The S domain is another dimension. You have your differential equation, you throw it to another dimension. In that dimension, there is no derivatives. You solve it very easy, and then you bring back the solution of that domain and on that dimension to this dimension, and you get the solution. So this is what we are going to cover. Let's do one example of a differential equation. All right?